Hi, and welcome to the first part of Exam 3 for Carlos Coe's Transport 2 class. In this part of the exam, we're going to go through and explain the Lewis relationship and how we are able to find that and apply it through an example problem where we have pretty much water and air going through a pipe. Some of that water is being evaporated to develop into moist air, and how we're going to pretty much explain through this and understand the Lewis relationship to apply it later in the exam as well. So, starting off, we are given that we need to look into and understand the Nusselt-Sherwood relationship, which I already have put up here, and the Nusselt equation, and that's pretty much rewritten as A multiplied by the Reynolds number to the power of B multiplied by the Prandtl number to the power of C. And this is all over the Sherwood number, which can be rewritten as A to the power of Reynolds power, or A2 times the Reynolds number to the power of B multiplied by the Schmidt number to the power of C. And so the first thing that we really should do if we're going to try to understand the Lewis relationship is we're going to try to work our way to getting to the Lewis relationship. And so we're going to have to go through and redefine Nusselt number, Sherwood number, Prandtl number, and Schmidt number. And this is because if we're looking at this equation here, A's cancel out and the Reynolds number to the power of B's cancel out. So really we're left with Nusselt number over Sherwood number equals Prandtl over Schmidt to the power of C. So that's what we're currently dealing with and we're trying to look at since those do cancel out. And starting with the Nusselt number, you can redefine this by making it as the heat coefficient multiplied by the diameter, all divided by the mass transfer coefficient, which is Kc. And so this is really what we're going to try to work it together, and we're going to try to get to this so that's isolated and we can have that heat transfer coefficient over the mass transfer coefficient, so we can see pretty much how much heat is transferred per some sort of mass. Really, we could say it's a kilogram, we could say it's a gram, but it's really dependent on whatever we have. But this is really the main equation that we're going to try to work through and try to isolate from the rest. And so now that we're looking at the Sherwood number, we go to that one. That is going to be the thermal conductivity, K, also multiplied by the diameter. But the only also the other difference is that this is going to be over the diffusion constant from flowing between diffusion components A and B. So now that we have these, we can actually simplify them out and pretty much combine them. And so this Nusselt over Sherwood, I'll rewrite this here. This Nusselt over Sherwood, we can pretty much keep this and do a keep change flip type of equation and get this to become more condensed. And so these diameters will cancel out and we will be left with the heat transfer coefficient multiplied by the diffusivity constant from A to B all over the thermal conductivity multiplied by the mass transfer coefficient. So this is what we have currently for the Nusselt over Sherwood relationship if we're going to go through and rewrite it in different variables. And so we couldn't get that at the moment. And so the next thing we want to do is we're going to go and define this right side of the equation, the Prandtl over the Schmidt number. And so the Prandtl number can be written as the kinematic viscosity all over the, I think it's the mass transfer coefficient. No. That's the Schmidt number. This one's the thermal conductivity, alpha. And so that's the actual equation that we can have for the Prandtl number. And pretty much going through and having for the Schmidt, it's pretty much the same thing, the kinematic viscosity, but instead it's going to be over the diffusivity constant from A to B. So now that we have these and what we want to look at, we can also combine these two in the same way that we did this, where we will have the Prandtl over the Schmidt like we have in the problem that we condensed to. And instead of this, so these kinematic viscosities will cancel out. So we'll keep this, change this, flip that, multiply it. So we are left with the diffusivity constant from A to B all over alpha, the thermal conductivity. And so that's pretty much what we're left with at the moment. But the thing is that we can actually go through and expand this and get rid of this thermal conductivity coefficient as well. And so what we can do is we can actually change this into the diffusivity constant. So I'll just rewrite it right underneath the Prandtl over Schmidt equal to the diffusivity constant from between components A and B, and then this will be multiplied by the density and the heat capacity, and then this will also be all divided over the thermal conductivity, I believe. That looks right. I think that's, I'm pretty sure that's right. Thermal conductivity. And so now that we can pretty much reset these equations up, we can also, actually, one thing before I actually move on. This is also going to be an important part of this is going to actually be equivalent to 1 over the Lewis number. Once again, this is the relationship that we are going to be having because this right side of the equation, if we want to look at it in this way, which is what we're going to want to do, we can see it as the Nusselt over the Sherwood number is equal to 1 over the Lewis number to the power of C. And so that's going to be actually important over here. But so first off, before we actually look into that and do that, we have the numbers over here from what we can really have and apply for, that's not supposed to, I just realized this is not supposed to be the mass transfer coefficient. That's a heat transfer coefficient, my apologies. But so we can look at these, and these are pretty much values that are given to us from moist air content. Since we know that some of this water is going to be evaporating up into the air as it travels through the pipe, we know that we can just go ahead and assume these numbers. And this will be helpful with us in trying to estimate what we should be setting this right side of the equation is equal to. And so if we plug these three numbers into here to get the Prandtl-Schmidt relationship, this is going to actually come out to be about 1. So we know that 1 over the Lewis number is also going to be equivalent to about 1. And so that helps us here when we're actually like looking at it and trying to understand this whole situation. But what we really need to do is that we need to somehow correlate these mass transfer coefficient and the heat transfer coefficient somehow to this Lewis number. But we can also rewrite this and look at it as just 1 second. I want to make sure this is right. I think I'm pretty sure. Yeah, it has to be right now. Okay, so we want to rewrite it in these terms, where we have H D A B over the Sherwood, which is K K C, equal to 1 over the Lewis number. And so we'll have this. But in reality, we can actually change this around and we can just look at it from the aspect of getting rid of the DAB and the KC, dividing that over. And we can be left with the mass transfer or the heat transfer coefficient over the mass transfer coefficient is equal to and relevant to 1 over rho density multiplied by the heat capacity. And so this is actually going to be the Lewis correlation we are wanting to look at and we want to define in general. And so after we rewrite these and pretty much submit the values for what we want to, how we want to look at these, we can actually rewrite it in terms of whatever the heat transfer coefficient is over the mass transfer coefficient. And then this will be equal to 1 over rho times Cp, which we know is approximately 1 based on the values that we can assume and plug into this equation. And so that's pretty much interesting, and it tells you that because the volumetric heat capacity, which is this value right here, is going to be about 1. And this, we can only know this because of these values that we assumed and we brought in and for the Lewis number relation, and we can see that the Lewis correlation, Lewis relationship is approximately 1. And we're going to be using this further when we go into the further parts of the exam 2, 3, 4, and 5. I will also explain this further in detail as well in the future, but this is about concludes part 1 of the exam, and I'll see you in part 2.